Yes.
Will you be teaching the earthquake engineering class?
Yeah, that will be two springs from now.
2 springs from now?
Yeah, not next spring. Spring.
Okay.
Yeah.
Okay. I was just curious as to when that was going to happen.
Yeah, I'll be co-teaching it with Professor Said.
Okay.
So it's 50-50.
It's going to be like a geotechnical side and a structural side?
Yes.
Okay.
Yeah. So most probably, if it's like 2 lectures a week, he's going to be giving one, and I'll be giving the other.
Okay.
So it's 50% on
For
this
each
side,
one of you?
50%.
Okay. That's
So
awesome.
they are completely different topics.
Will the test be made together?
We didn't agree on this yet because it's not even next spring. It's
Right. Well, still, we're looking at graduate into the seismic side,
Yeah.
and I would feel like would help. But it's 2 years from now too, so.
So I've done this before. Another professor not here. So what we did is it's just one final, but it's like separate questions. So once testing is finished, we just separate the question who creates this part. But you take just one final test.
Right. Yeah, that is neat. They're offering earthquake engineering in 2 springs. I'm not going to be here.
What's that?
Dylan, what time do you get done
What
today?
you said? Your class.
Class.
I was supposed to say that.
I get off at 5. I have a dentist appointment at 5.
At 5?
Yeah.
Okay, good.
And then however long that dentist appointment takes.
They have elections today at ASUCE that I have to go to at 5. But hopefully it works out.
Well, I figure that dentist appointment will probably be about 6.
We'll see.
I assume. I don't know how long it takes. Even if you're not done, I'll go eat supper. And then,
Just go eat supper. Yeah, that's fine. I figure I'm gonna be up pretty late tonight.
same.
But I got off work tomorrow night, so.
Then we got a rain gauge we gotta go check tomorrow too.
That's what that's.
That's fun.
The other bartender isn't going out of town. He's like, I'll work. And I'm like, thank gosh. Thank you.
Is that tomorrow? Are you talking about tomorrow night? Yeah, that'll make it a little easier on you.
That adds 7 hours to my day.
Yeah.
Sometimes 8 hours.
I'll say you're not having to pull a double. You're not pulling a double.
I'm working Saturday, but
Oh,
not
okay.
Friday.
Well, then that helps. Yeah. I'll leave once I do that.
Yeah, that's why I need more stock out there.
Yeah, 10. Let's do 4.
You used to work for
Me? Yeah. Matt. I work average.
I'll probably would have relied.
It's pretty good.
It's horrible. Trying to manage these people.
Mine's not good, and then offenses. We're out there.
This is like 10.
Hey, I'll just one second. You think you'll be able to? I asked him, he said, for me, he's like, yeah, he's like, are you trying to be
Feeling right there.
nice?
Okay, so good morning, everyone.
Today, in our last lecture, we're going to finish the how to calculate the deflection in beams. Okay. So last time we started the double integration method. Today we're just going to solve one extra example on the double integration method, and then we're going to learn another method for calculating the deflection called the method of conjugate beams. So what's the double integration method? Again, just a reminder, double integration method is based on this equation, deflection at any point V, the second derivative of the deflection at any point, okay, V is equal to m divided by EI. So you just write the equation for the moment, you divide it by EI, you integrate it once, you find the rotation for theta, the slope, okay, any point, you integrate this once again, you find the deflection or the equation that gives you the deflection at any point, okay? We did this for two examples last time, this example and this one over here. And then today we're going to see solve another example using the double integration method. So what are the steps? First step is writing the equation for the moment, okay? So now, to write the equation for the moment over here, how many, is it just one equation that you need to write to represent the moment at any point? Do you remember when you wrote the equation for the moment, right? It's actually two. You need two equations, not just one, okay? Why? Over here, if this is the distance x1, okay? Any section over here, okay, you have a certain equation, but then over here you have a different equation, because here you're going to have a reaction that has to be added. So let's start by finding those reactions first. So first step here, finding the reactions. So here you have a reaction AY, here you have BY. Definitely there is a horizontal reaction as well, AX, but AX is not going to give any moment, okay? So, and it's actually 0. So taking the summation of the moments about point A equal to 0, you have here P times its distance to point A, which is 3A, and this should be equal to BY times its distance to point A, which is 2A. So BY is equal to 1.5 P. So this is 1.5 P, and then the summation of the forces in the y direction is equal to 0. So AY is equal to negative 0.5 P. What does negative mean? That your assumption was wrong. It's actually downwards, okay? And this is 0.5 P. Okay? So it's not upwards, it's downwards. So now, let's write the equation for the moment. As we said, you have two locations. For x1 equal to 0 to 2a, you're going to have an equation. And then for x2 equal to 2a to 3a, this is from point here, point A to B, and here this is from point B to point C, okay? You have two different equations. So which equation we're going to use, okay? Here, what's the equation for the moment? From A to B, what's the equation of the moment? It's this force, the 0.5 P, okay, times its distance x1. So it's negative 0.5 P x1. That's the equation for the moment. What about the equation from B to C? Taking a section over here, it's again the same, 0.5 P times x2, so negative 0.5 P times x2, but now we have the reaction By, okay, that has to be multiplied by its distance to that point, okay? So we have 1.5 P, okay, times its distance, which is x2 minus 2a. Okay, this distance over here is x2 minus 2a. Okay, So now I have two equations for the moment. Which equation should I use to integrate twice to get the deflection? Actually both, okay? If you want to find the deflection at any point from point A to B, then it comes from the integration of this equation. If you want to find the deflection at any point from B to C, then it comes from the integration of this equation of motion, of this equation for the moment, okay? So let's do the integration for both of them, okay? So here, theta is equal to the integration of m dx. So it's the integral of negative 0.5 p x, okay, dx. So how do you integrate this? It's negative 0.5 p x squared divided by 2 plus c1, right? And then you integrate it again. V, the deflection at any point, is the integration of that again. So the integration of negative 0.5 p x squared divided by 2 plus c1 dx. So it's negative px cubed, and this 0.5, it's and half over here, that's 1/4 times 3, so this is 12, plus c1x plus c2. So that's the equation that gives you the deflection at any point, okay? I just here forgot something. It's EI here. I have to divide by EI, okay? So here we have 1 divided by EI multiplied by everything. So just 1 divided by EI. 1 divided by EI. Okay? So that's the deflection at any point. Okay? But how much is C1 and how much is C2? How can you get the values of C1 and C2? What did we say to find the values of C1 and C2? You need some boundary conditions. You need to have some information to help you find C1 and C2. So from A to B, is there any boundary conditions, any deflection, any rotation that you know? From A to B? Yes, I know the deflection. How much is the deflection at point A? When this beam deflects, this point is going to move down like this, and here there is a support that prevents the beam from moving, and then here there is a support that prevents the beam from moving. So this is the deflected shape. This is the expected deflected shape, right? So how much is the deflection at point A? There is a support, so it's 0. Okay? And how much is the deflection at point B? 0. So those are the two boundary conditions that I'm going to use, okay? So at x equals 0, that's point A, okay? V is equal to 0. That this is point A. Point A is a support. You have a support, okay? So it prevents the deflection. So let's plug those numbers. Put V equal to 0 and put x equal to 0. So you're going to have just C2. So C2 is equal to 0. So now the equation for the deflection, V, is 1 divided by EI multiplied by negative px cubed divided by 12 plus C1x. C2 is equal to 0. Now I use the second boundary condition. So here this is the boundary conditions. The second boundary condition at x equal to 2a. The deflection is equal to 0 as well. Why? Because you're at point B where you have a support to prevent the vertical deflection. Okay? At point B there is a support. So let's just plug the deflection equal to 0 and then just put x equal to 2a. So this is 2a cubed divided by 12 plus c1x, which is 2a. So now from this equation you can solve for c1, and c1 is going to be equal to p a squared divided by 3. That means that the deflection at any point, okay, from point A to point B, just 1 divided by EI, negative P x cubed divided by 12 plus C1, which is PA squared cubed times x. This is the equation for the deflection at any point from point A to point B. Can you use this equation to find the deflection at point C? Can you use the equation that we just wrote to find the deflection at point C? No, it's only valid from A to B. You can use it to find the deflection here, 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 but just in point B. Any point over here, you need to find another equation, okay? That comes from the integration of the moment in this part, from B to C, okay? So all what we did over here was kind of useless, okay? Right? You didn't need all of this, okay? So actually it's not useless. We're going to see that it's not useless, okay, in a moment. But it seems useless now, okay? Actually what you need to do is integrate the equation from point B to point C. So now we have this moment, okay? We need to integrate it, okay? So theta is the integration of m divided by EI dx. This is theta in the segment from point B to point C. So this is equal to the integral of negative 0.5 px, 1 over EI is 1 over EI over here, plus 1.5 p x2 minus 2a. I just put x instead of x2 dx. So 1 divided by EI, and let's do the integral here. We have px squared divided by 2, so that's 4. Negative px squared divided by 4 plus 1.5 px squared divided by 2, and then minus 3pax. Okay? That's the integral over here. Okay? Anything left? Anything missing? Constant. So plus C3, a third constant. Okay? And then let's find the deflection. The deflection is the integration of theta dx. Okay? So that is equal to 1 divided by EI, and then the integration over here. So let me write it on a new line. 1 over EI. And then let's integrate it just term by term. So negative px cubed divided by 12 plus 1.5 is just 3 divided by 2. Okay? Yes. Okay? So 3 divided by 2, so it's 3 divided by 4. 3 divided by 4, and here we have px cubed divided by 3. Okay, so the 3 cancels with the 3, minus 3pax squared divided by 2, plus c3x plus c4. Okay? Let me make sure we have everything correct over here. I guess I have something wrong here. X squared. Okay, so okay, that's fine. So now we have the first two terms. We have px cubed and px cubed. So just combine them together. We're going to have 1 divided by EI, okay? And then we're going to have px cubed divided by 6 minus 3pax squared divided by 2 plus c3x plus c4. Okay? This is the equation that gives you the deflection at any point. Okay? From B to C. But here we have another two constants, C3 and C4, that we have to find. Okay? How much is C3 and C4? How can you find them? How can you find C3 and C4? You need boundary conditions, some deflection or rotation at some point from B to C that you already know, and just you plug it in those equations to solve for C3 and C4. What's so here? From B to C, in this segment over here, is there any deflection or rotation that you know? What?
At B, deflection equals 0.
At B, the deflection is equal to 0. Okay? We used this before in segment AB, but we can still use it again in BC. That's fine. Point B is common, okay, between the two segments. So the boundary conditions now, so at x equal to 2a, v is equal to 0. This is point B. Okay? So let's plug the numbers. V is equal to 0 when x is equal to 2a. So 1 divided by EI P 2a cubed divided by 6 minus 3 PA, and x is 2a squared divided by 2 plus C3x, which is 2a, plus C4. Did you find anything here? Are you able to use this equation to find C3 or C4? No, because it's an equation in two unknowns. C3 and C4 are unknowns. Okay? So let's write this as equation 1. Okay? So we need another equation. Right? What's the other boundary condition that you know? Theta at B equals to 0. Why? That was when you had a cantilever beam. When we had a cantilever beam, okay? So here, theta is equal to 0, and the deflection is equal to 0. But this is not a cantilever beam, okay? You don't have a fixed support over here, so the beam is allowed to rotate. There can be an angle of rotation over here, theta, okay? It's not equal to 0. What's the other boundary condition? If someone says that correctly, I will give him 1 bonus point. But don't look at the book.
Can't talk. The deflection at B is 0. Is that what you're looking for?
The deflection at B, yeah, we used this already.
Oh, okay.
The deflection at B is equal to 0. Okay? You need another boundary condition. What would that be?
B to C.
Some piece of information that you know. The slope, the rotation. Is the rotation anywhere here known?
X2 to 2a. X2 minus 2a. It's not between there, is it? Or not?
X2 minus 2a. This is the point here. Okay? What about it?
Do we not know? I guess we don't.
Theta times LBC. Is it theta times the length of BC? So
Theta times the length of the segment. Okay?
gives you the
Gives you the deflection over here. This is, you don't know the deflection over here, but no, again, this is not correct. Okay? Okay, the thing is, look, my question is, do you know the rotation theta at any point? Yes. It doesn't necessarily be 0. Okay? I know the deflection over here at point. How would I know this? It's point B. Point B is common between the two parts. I already know the deflection, the equation for the rotation here. I can use it to find the rotation at point B and then use it here as the boundary condition. Right? Point B is common. Whatever the rotation at point B that I get from segment AB is equal to the rotation in segment BC. Okay? It's the same point. Okay? So that's why, I told you this part seems useless, but now I'm going to use it. Theta here. I'm going to use this equation for theta. Okay? So here, the second boundary condition is theta b from the left part is equal to theta b from the right part. How much is theta b from the left part? It's this equation. Theta here is just 1 divided by EI multiplied by negative 0.5. Let me just copy it, okay? So 1 divided by EI negative P x squared divided by 4 plus C1, which we found as P a squared divided by 3. Okay? And at B, x is equal to 2a. So I have to substitute x equal to 2a in this equation. And then in the second part here, how much was theta? Okay? Theta in the second part is 1 divided by EI P x squared divided by 2 minus 3PAX plus C3. And I have to put x equal to 2a. Okay? So let's just do this here. So therefore, 1 divided by EI, and just negative P, 2a squared divided by 4, plus P a squared divided by 3 equals to 1 divided by EI, P 2a squared divided by 2 minus 3PA x, which is 2a plus C3. What can you get from this equation? You can find the magnitude of C3. So therefore, C3, okay, is going to be equal to 10 divided by 3 PA squared. And then substitute C3 into equation 1. What's equation 1? It's the equation that we had here, where you had C3 and C4. Now you know how much is C3. You can use it to solve for C4. So therefore, C4 is going to be equal to negative 2PA cubed. Now I know the deflection. So therefore, from point B to point C, the deflection is equal to P divided by 6EI x cubed minus 3PA divided by 2EI x squared plus 10, this was C3, 10 PA squared divided by 3 EI x minus C4 divided by EI. So that's the deflection at any point, okay, from B to C. Now I would like to find the deflection at point C. The deflection at point C, okay, let's name it or call it VC. Just put the location of point C. How much is the distance of point C? How much is x at point C? 3a. So therefore VC is equal to P 3a cubed divided by 6EI minus 3PA divided by 2EI 3a squared plus 10 PA squared divided by 3EI x, which is 3a minus 2PA cubed divided by EI. All the terms have PA cubed, okay, divided by EI. Just sum the factors over here. It's going to be negative PA cubed divided by EI. That's VC that you were looking for. The deflection at point C. Any question? Okay, great. So now let's move ahead to another method for calculating the deflection. Okay? The method of conjugate beams. Okay? What's the rationale about the method of conjugate beam? Okay? What's the basis for it? The theory behind it. Do you remember, or before that, how do we calculate the conjugate beam? Or sorry, how can we calculate the deflection? What do we know? You have to calculate m, okay? And then you divide it by EI, and then you integrate this, okay, right? So you have theta is equal to the integral of m divided by EI dx, right? And then you integrate this again, okay? So here integration, and you have to integrate it again to find v, the deflection, right? That's the theory that we have. So you have some function m, you integrate it, you find theta, you integrate it again, you find the deflection. So here, I don't know if this is going to click with any one of you. Does this remind you of something that we used to do earlier this semester? You have some function, you've integrated, you find something else, and then you integrate it again, you find something else. Where did we used to do this?
Sure.
Exactly. So if that reminds you, when we had W, okay, a load on the beam, when you integrate it, you find the shear, V capital here. Don't mix those together. The V capital is not the deflection. This is the shear. It's just the integration of negative W dx, right? And then you integrate it again, okay? You get the moment, M, which is the integration of the V dx. What? It's the same process, okay? It's exactly the same thing. If you know M, you integrate it, you find theta. If you know W, integrate it, you find the shear. You know theta, you integrate it, you find the deflection. You know the shear, you integrate it, you find the moment. It's the same, relationship, okay? So, what if, since it's the same relationship, if I assume or treat the moment as a load on the beam and draw the shear for that load, this new load, okay? This shear represents what? Represents theta. If I draw the moment for that load, okay, new load, I'm getting the deflection, right? So here there is an analogy between them. Assume the moment is like a load. Assume that the moment, the bending moment that you have, is a load. And then draw the shear, okay? For that load, you're finding theta. Okay? And then find the moment for that load, you're going to be finding the deflection. Okay? So that's the method of conjugate beam. So let me draw this here, or write this here. So draw M divided by EI, okay? And then consider it, consider this moment, okay? This bending moment drawing that you have, consider it as a new load on a new beam. We're going to call this on a conjugate beam, okay? So we're having a new beam, okay? And then the shear and the moment for the conjugate beam represents the slope or the rotation theta and the deflection V. Okay? It's that simple. Okay? So let's see an example over here. We're going to solve two examples. Okay? So the first example here is example 814 in the textbook. We have a beam that looks like this, simple beam. Okay, we're going to start with the simplest thing over here. And here at this point we have a load of 8 kilonewtons. And those distances or dimensions, 9 meters and 3 meters. This is point A, B, C. We're given E. E is 200 gigapascals. We're given I. It's 60 times 10 to the power 6 millimeters per 4. And we're required to calculate the maximum deflection in the beam using the method of conjugate beams. Okay? So how can we do this? What does the method of conjugate beam say? It says draw the bending moment diagram. That's the first step. You have to draw the bending moment diagram. Okay? And then consider this bending moment diagram as a load. Okay? So let's start with the first step. We need here to draw the bending moment diagram for this beam. How to draw the bending moment diagram for this beam? I'm not interested in drawing the shear, just I want to draw the bending moment diagram here. How can you draw the bending moment diagram? I've learned this throughout the semester. You have to find the moment at the critical points. What are the critical points? A and B start and the end of the beams. How much is MA and how much is MB? 0. And what else? What are the other critical points? C, because you have concentrated force at point C. So we need to find MC. You can take a section at point C and find this from the left part or the right part. So to do this, we need to find the reactions first. So now the first step, find the reactions. So we're going to find the reactions. We're going to find those two reactions, or at least one of them. So we're going to find By, it's going to be equal to 6 kilonewtons, and Ay is equal to 2 kilonewtons. Okay? So the first step over here, step 1, draw the bending moment diagram. So to draw the bending moment diagram, we're calculating the moment at the critical points. MA is equal to 0, MB is equal to 0, and MC. Can someone tell me now how much is MC? You take a section at point C and then you calculate it from the left part or the right part. How much? How much is MC? If you take that long to find MC, that's a problem. How much is MC? 18. It's either from this side You take a section over here, so it's 6 times 3. Or you take a section and consider this side, it's 2 times 9, it's 18. Okay? So MC is 2 times 9, so it's 18 kilonewtons meter. Okay? So now let's draw the bending moment diagram. Here the moment is 0, here it's 0, at point C it's 18. Kilonewtons meter. What's this? This is the bending moment diagram. Now, look, all the method of conjugate beam is just described in those 2 lines. If you know, just read those 2 lines. Draw and divided by EI. Did we draw the moment? Yes, we just have to divide it by EI. So I'm just going to draw it again by dividing it by EI. It's the same moment, but just 18 divided by EI. That's all. Okay? And then consider it as a new load. So this is a load on a conjugate beam. So now, this is not a bending moment. This is a load. Okay? I will consider this as a load applied on the conjugate beam, on a new conjugate beam. So I have a beam that has this load applied on it. What's this beam? It's a conjugate beam, the conjugate beam, not the real beam. Okay? This is the conjugate beam, not the real beam. Okay? We're done with the real beam. And now, once we have the conjugate beam, the shear for this conjugate beam represents what? Is it a shear? No. The shear is the rotation, theta. The moment for this conjugate beam, is it a real moment? No. It's the deflection. That's the method of the conjugate beam. Conjugate beam, okay? So now, let's quickly, okay, consider this conjugate beam, okay? The only thing here that you have to take care of, okay, when we did this analogy, M divided by EI, okay? There was here just a negative sign. There was no negative sign over here. Right? So actually, to be similar, M divided by EI has to be equivalent to negative W. Okay? So how would we do this? When we're dealing with this load, someone would say, okay, just put it on the opposite side. That's negative. Okay, that's fine. Or I'm going to just, when I find the concentration of it, okay, the equivalence of it, I'll just put it in the opposite direction. Okay? So for example, now, you have a load that looks like this, okay? Let's find the equivalence of it. We have 2 loads. We have a load here, triangular load here, and a triangular load here. What's the equivalence of them? Here you have a triangular load. It's 1/2 the base times the height, right? So it's 1/2 18 divided by EI times the base, which is, how much was the base here? 9. So that's equal to 81 divided by EI. A very important thing here. Why did I put this load upwards, not downwards? Why did I put this load upwards, not downwards? To take care of the negative sign. Okay? M is equivalent to negative W, not W. Okay? So I have to put it in the opposite side. Okay? And then here, this load is how much? 1/2 the height times the base, which is 3 meters. So this load is equal to 27 divided by EI. Okay? Now I have this beam with those 2 loads. Can you tell me what are the dimensions of those loads, the distances? How much is this distance? How much? 6 meters. And how much is this distance? 2 meters. So how much is this distance? The total length of the beam was 12, so this is 10 meters. Okay? Now we have new reactions. We have a reaction here, AY and BY. Do you know how much is AY and BY? Someone would say, yeah, we calculated this before. It's 2 kilonewtons and 6 kilonewtons. No, that is a completely different beam. That's the real beam. Now we're talking about the conjugate beam. You have to find AY and BY on the conjugate beam. Okay? So just take moments about point, the summation of the moments about point A. Okay? So now just to be precise, let me write this so that you can study from it. Step 2, okay? Use M divided by EI as load on the conjugate beam, okay? So taking the summation of the moments about point A equal to 0, okay, you have 81 divided by EI times 6 plus 27 divided by EI times 10 minus BY, okay, but here it's positive, it's going to be, let me put it like this so that it's downwards and downwards. So minus BY times 12 equal to 0. So BY is equal to 63 divided by EI. So this is 63 divided by EI. And then the summation of the forces in the y direction is equal to 0, so you can find AY. So AY is going to be 45 divided by EI. So now I know how much is this. It's 45 divided by EI. Okay? Those are the actions on the conjugate beam. Now, let's see step 3. What's step 3 and step 4? The shear on the conjugate beam is the slope, the rotation. Okay? So let's see let's draw the shear force diagram. So here the slope theta is the shear. Okay? So if we want to draw the shear force diagram, okay? The shear force diagram here represents theta. Okay? So how to draw the shear force diagram? Okay? How would you draw the shear force diagram? You start from the left, okay? AY is going downwards, it's 45. You go down, 45 divided by EI. And then you have this load going up, okay? How much was it? It's 81. So I'm going to go from $45 up, okay? 81, and then I'm going to go up again with 27, okay? And then here I'm going to go down with 63 divided by EI. That's point C here. This is how you draw your shear force diagram. Now, if I ask you, how much is the rotation at point A? How much is the rotation at point A? This beam would deflect like this, right? There is an angle of rotation here, theta A. There is an angle of rotation here, theta B. How much is theta A? How much is theta B? Theta A is the shear at point A, right? On the conjugate beam. So it's negative 45 divided by EI. That's theta A. How much is theta B? It's this value, 63 divided by EI. How much is theta c? This thing. Okay? So now, this is the rotation. If you want to find the slope at any point, just find the shear at that point, and that's it. And what about step 4? The deflection V is the moment. Okay? So how would the bending moment look like? Bending moment here. The bending moment for what? For the conjugate beam. You have a beam with those loads applied. How can you find the bending moment like that? The moment here is 0, the moment here is 0, right? And then what the moment, would it increase or decrease? Let's see here. So from the shear, okay, you have negative shear, so it's going like this. And here you have the shear equal to 0. So here you're going to have the maximum bending moment, and then it's going to decrease. So here you have M max, or I'm going to call it V max, the maximum deflection. That's the maximum deflection. Where would the maximum deflection happen? Where theta is equal to 0. Okay? So where's that point where theta is equal to 0, or the shear on the conjugate beam is equal to 0? That's what we want to find V max, the maximum deflection. Where's that point? Is it at point C? Is it right at the middle of the beam? How can you do this? How can we find the point where theta is equal to 0? Let's take a section at that point. So here, you have AY, which was equal to 45 divided by EI. I don't know how much is the distance from point A to the point here where theta is equal to 0. Okay? We had a load. Okay? How much is the intensity of that load at that point? How much is the intensity here? The intensity of the load at point C was 18 divided by EI. That's the intensity at point C. So now at the distance, this point here, C, the intensity is 18. This distance is 9. So now if we're just at the distance x, how much the intensity would be? 18 divided by 9 multiplied by x. Okay? So the intensity over here is 18 divided by EI divided by 9 and multiplied by x. So the intensity is 2x divided by EI. Okay? Now, how much is this load? This load is equivalent to a load that is going up, and it's a triangle load, so it's 1/2 the base times the height. So 1/2 the base. How much is the base distance? X. And how much is the height? 2x divided by EI. So that's the load over here. Okay? I took a section over here at this point. So there is a shear force, there is a moment, and there is a normal force, right? At this point, how much is the shear? 0. For this shear to be 0, those two forces has to be equal and opposite in magnitude, right? So at the point where the conjugate shear, not the real shear, the conjugate shear is what? Is theta, okay? Is equal to 0, the deflection is the maximum. So just equate those two forces. AY, which is 45 divided by EI, has to be equal to that force, which is x squared divided by EI. So therefore x is equal to square root 45, so it's 6.71 meters. That's the point where the maximum deflection is going to be. Okay? So now, I know the location. I need to find the deflection at that point now. What's the deflection? The deflection is the moment. Can you find the moment at that point? Can you find how much is this moment? Can you do this? How much is this moment? 45 times x, okay? It's negative plus this force, which is x squared divided by EI times this distance. How much is this distance? One-third x. Okay? So now, M maximum on the conjugate beam is equal to the maximum deflection. I'm going to call it Vmax. So Vmax is equal to negative 45 divided by EI times the distance x, which is 6.71 meters, plus the force, which is x squared divided by EI times x divided by 3. So it's negative 201.2 divided by EI kilonewton meter cubed. Okay? That's the maximum deflection. So Vmax, the only step left here is how much is EI. So here this unit is kilonewton meter cubed. E was given in the problem statement, it's 200 gigapascals. Okay? So I have to use the same units here. 200 gigapascal. What's a gigapascal? It's 10 to the power 9 pascals. What's a pascal? It's Newton per meter squared. I cannot use Newton. I want to use kilonewton. Okay? So I'm just going to divide by 1,000. So instead of multiplying by 10 to the power 9, I'm just going to multiply by the 10 to the power 6. Okay? To change the gigapascals to kilonewtons per meter squared. Okay? So that now is in kilonewtons per meter squared times I, the moment of inertia. The moment of inertia was given as 60 times 10 to the power 6 millimeters per 4. 60 times 10 to the power 6 millimeters per 4. Can I use millimeters per 4? Is the units consistent? No, I have to use meter per 4. Okay? So how to change from millimeter to meter? Divide by 100. But now I'm not changing from millimeter to meter. I'm changing from millimeter to the power 4 to meter to the power 4. So I'm dividing by 100 to the power 4. Okay? So 10 to the power negative 8. Just multiply by 10 to the power negative, from meter to millimeter, this is not 100, this is 1,000. So 1,000, 1,000 power 4, that's 10 to the power 12. Okay, so 10 to the power negative 12. So now we're going to have the deflection equal to negative 0.0168 meters. Okay? Or dividing by, or multiplying by 1,000. 1, 2, 3. Okay, it's negative 16.8 millimeters. That's the deflection, the maximum deflection. The maximum deflection is not at point C. Okay? As you see here, the maximum deflection was not at point C. You had to find the location for the maximum deflection where the shear is equal to 0. Which shear? The shear on the conjugate beam. Any questions? Okay, so now, a very, very important topic, okay, before we solve the other example. When we drew the conjugate beam, the real beam was simply supported beam, and when we drew the conjugate beam, we drew a simply supported beam, okay? So does the conjugate beam always look the same like the real beam? No, okay? There is a table, okay, that tells you how does the conjugate beam look like, okay? So let's see this table. So now, how does the conjugate beam look like? Okay, the structure of the conjugate beam. So here, there is this table. I'm going to give it to you on the test, by the way. Okay? So the real beam and the conjugate beam. If you have a pinned support at the end, pinned or roller support at the end, pinned or roller support at the end of the beam. It has to be at the end of the beam, okay? Then in the conjugate beam, it's going to remain the same, okay? Pinned or roller support at the same location, okay? So that's the first case here. And then, if you have a fixed support, okay, fixed support, okay, in the real beam, on the conjugate beam, that becomes a free end. The fixed support becomes a free end. Why is that? Because here, when you have a fixed support, how much is theta at the fixed support? How much is the deflection? 0. So the moment at the shear on the conjugate beam has to be 0. How would you ensure that the moment at the shear on the conjugate beam is 0? If it's a free end, the shear here is going to be 0, and the moment here is going to be 0. It has to be a free end so that the moment and the shear becomes 0 on the conjugate beam. Okay? And then, if you have a free end on the real beam, a free end can have a deflection, right? Can have a rotation. So how would you have this on the conjugate beam? A point, an end point where you can have a moment and a shear. So you need to have a support that gives you a moment and a shear, okay? On the conjugate beam. So a free end becomes a fixed beam or a fixed support. Now, if you have a pinned or roller support intermediately in the beam, not at the end. So here, intermediate roller or pinned support. How would that look on the conjugate beam? It becomes an internal hinge. Why is that? Here, how much is the deflection? If you have a support, how much is the deflection of the support? 0. So the moment in the conjugate beam has to be 0. How come the moment in the conjugate beam becomes 0? If there is an internal hinge, you are sure that the moment at that point is going to be 0, right? And the opposite. If you have an internal hinge, okay, in the real beam, on the conjugate beam, it becomes a support, an internal pin support. Okay? So that's the table, okay, that gives you the, the shape of the conjugate beam. So let's solve another example here. Example 8.16. So in example 8.16, we have a beam that looks like this. We have a load here, right in the middle, it's 8K. We have a moment here that is 30 Gibbs feet. And those dimensions, this is 15 feet, this is 12 feet, 12 feet. Okay? This is point A, point B, and point C. Okay? Here we're required to find the deflection at point B and theta B, the rotation, point B left and theta B right. It's the same point. How come there is two different rotations at point B? Because there is an internal hinge. So when this beam deflects, let's see here, it's fixed over here, and then it can deflect like this. So this is VB, the deflection at point B. But it's an internal hinge. An internal hinge, the beam can be broken at the internal hinge. It's a hinge, okay? Both parts can rotate independently. So there are two. So here you have theta B left, and here there is theta B right. Different angle, completely different angle, both sides, because the hinge allowed this to happen, okay? So now, how can we do this? Using the method of conjugate beam. How can you solve this problem? What are the steps? Draw the bending moment diagram, consider it as a load, put this load on the conjugate beam. The shear for this conjugate beam is the rotation, the deflection is the moment. That's it. So the first step, I have to draw the bending moment diagram first, okay? So the first step, step 1 here, draw the bending moment diagram. So I would like to draw the bending moment diagram. So to draw the bending moment diagram, I'm going to draw the free body diagram first for each part here. Here I have 8K. Here this is a fixed support, so there is AY, there is MA, and there is XA, which is going to be 0. Here we have a vertical force BY, and here we have a vertical force CY, and this is 30 Gibbs feet. Okay? So here we're going to have a BY that is equal and opposite to that BY. So this is the free body diagram for each of them, for each part. Okay, I just broke it at the hinge. Now solving over here, okay, taking the summation of the moments about point B equal to 0, you're going to find CY. So CY is going to be 30 divided by that length, which is 15, so it's going to be 2K. And then the summation of the forces in the Y direction equal to 0, you're going to find BY, it's equal and opposite to CY, so it's 2K as well. And then this one is the reverse of it, okay? And then here the summation of the forces in the Y direction is equal to 0, so AY is equal to 6K. And then the summation of the moments about point A is equal to 0. You're going to find MA is going to be equal to 48 Gibbs feet. I'm just finding the reactions, okay? Nothing more than this, okay? Now I would like to draw the bending moment diagram. How would I draw the bending moment diagram? Find the moment at the critical points, okay? I'm going fast here because we're just repeating the steps that we did earlier many times, okay? So now, I would like to draw the bending moment diagram. How to draw the bending moment diagram? This is point A, B, C. Find the moment at the critical points. What are the critical points here? Okay? There is point D here, okay, where there is a load applied. So the moment at point A is negative 48. The moment at point C, there was a hinge, so the moment here is 0. Point C, you had a concentrated moment here of negative 30, so MC is negative 30, it's not 0. So negative 30. And here it's 0. So from B to C there is no load, so you have a straight line. How much is the moment at point D? I have to calculate the moment at point D. Okay? This is point D here. So I have to calculate the moment at point D. How much is the moment at point D? Take a section and study this part. It's 2 times this distance. Okay? How much is this distance? 12 feet. So that means that MD is 2K times 12 feet. So it's 24 Gibbs feet. It's positive. Okay? So now this is 24. I'm just going to connect them with straight lines because this is how the bending moment diagram look like. Okay? This is the bending moment diagram. What would you do with this bending moment diagram? Divide it by EI and consider it as a load. So I'm just going to divide it by EI, divide by EI, divide by EI, and consider it or treat it as a load on the conjugate beam. How does the conjugate beam look like? How does the conjugate beam look like? It depends on how the original beam looked like. You had a fixed support here. On the conjugate beam, this becomes what? Free air. You have an internal hinge here. On the real beam, this becomes what? Pin support. You have a pin support at the end. It stays the same, okay? So the conjugate beam looks like this. It's a free end here. You have a support here and a support here. What's this? It's an overhanging beam, okay? With this load applied on it, okay? So we have an overhanging beam that looks like this with those loads applied on it, okay? So now we would like to find the deflection at point B. What's the deflection at point B? The deflection at point B is the moment at point B. Okay? The deflection VB is equal to MB. How can you find the moment at point B? Just take a section at point B over here and study this part. So what are the loads that we have here? We have those distributed loads. So I have to find the equivalence of them. So how much is this load? And how much is this load? And how much is this load? So this one, it's going to be going downwards. It's 1/2 48 Gibbs feet divided by EI times the length. How much is this length? From A to D, the length was how much? 12 feet from A to D here. This is point D. It was 12 feet. So now this is 48, this is 24, so this is 2/3 the 12 feet. Okay? So this is 8 feet. Okay? So 8 feet here. So which is equal to 192 divided by EI. How much is this green force? 1/2 the height times the base, which is 4 feet. So this is equal to 48 divided by EI. How much is the red force here? 1/2 the base. How much is the base? The distance from D to B, it's 12 feet times the height, which is 24 divided by EI. So that is equal to 144 divided by EI. Okay? So now I can find MB. MB is this force times its distance, this force times its distance, this force times its distance to point. Okay? So MB is equal to, the first force is negative, so negative 192 divided by EI times its distance, which is, here you have from D to B, it's 12. So here you have 12, and then you have 4, and then you have 2/3 8. So 12 plus 4 plus 2/3 8 plus the other force, which is 48 divided by EI times its distance, which is 12 plus 1/3 4 plus the third fourth, which is force, which is 144 divided by EI multiplied by its distance, which is 2/3 the 12 feet. So this is equal to negative 2304 divided by EI in feet. That's the deflection at point B. It's the moment at point B. Okay? And then we need to find theta B left and theta B right. Okay? What's theta B left and theta B right? It's VB left, the shear at point B left, and the shear at point B right. How much is the shear here? It's the summation of all those forces, right? If you take a section here, the shear is going to be equal, from equilibrium, is going to be equal to those three forces. Okay? So theta B left is equal to the shear at B left, which is equal to negative 192 divided by EI plus this force, which is 48 divided by EI plus the third force, which is 188 divided by EI. So that is equal to 0. Okay? And then theta B right is equal to the shear at B right. Okay? So what's the difference between the shear at B left and B right? What's the difference between the shear at those 2 points? It's this reaction. So you have to calculate this reaction. Okay? So I'm not going to go how to calculate it. You know how to calculate the reaction. Just, take a moment about point C and don't forget this force. Okay? So there is a force here. Okay? This one is going to be 1/2 15 times 30. So it's equal to 225 divided by EI. So BY is going to be equal to 228.6 divided by EI. That's BY. So it's equal here to BY, which is 0 plus BY, so it's 228.6 divided by EI. Any question? I might have been, a little bit fast because we're just doing the same thing that we did, okay? It's just about the moment and shear, okay? We did this throughout the entire semester, okay? It's just you have to know that the shear on the conjugate beam is the rotation. The moment on the conjugate beam is the deflection. That's all, okay? Any question? Okay, great. So see you next Thursday on the test. Yes, definitely. This is going to be on the file. And it's fine. Okay? So most probably I can get the deflection problem or two deflection problems, one using the conjugate beam, one using the double integration method, influence line, okay, and the truss. Okay, so there's 4 questions on the final. Okay? The final is according to the university exam schedule, okay? So it's going to be Thursday, I guess it's 12:30?
12:30 to 2:30.
Right? Just check the exam schedule, okay? Of the register. So I guess it's 12:30. I'm not sure about it, but I guess it's 12:30. It's not the class time anyway, okay?
So on, when I came in, you said like the girders are in pounds per foot. So when I'm going to stats, I have like the girder and the load for each floor. So I got like 166 pounds per foot square. The girder's like pound per foot. So I've got the girder on there. But I take that and the 15 and then put it on top of that step of the girder.
No, I don't know.
I wanna get
Yeah, I'll
What's the 160 pounds per foot and what's the pounds?
okay, so that's the dead load of the girder.
The own weight of
The weight of the girder.
Okay.
If I'm trying to find like so here's for like this one right here.
Okay.
And then that's the girder.
Okay.
That's the weight of the girder.
Okay.
And then
It's an
for
80 pound per
and then
foot.
this
Yeah.
is the load of the entire floor.
Okay.
And then for
The dead load
of the entire
on
floor.
the, yeah, distributed over the area of the floor.
And then this was the 15 feet. So I'd multiply that by the 15 with what I top.
Like this. So it's gonna be prepared area. So
Right.
you look behind it. Okay? And this is 50, right?
Right.
Okay. So the own weight of the beam uniform load, okay, of 80 pounds per foot. That's the own weight. Okay? And then here you have 166 times
Times that
15.
15. Would I put that on top